are integer square matrices with determinant of plus or minus 1. And the inverse of a unimodular matrix is also unimodular, and the product of two unimodular matrices is also unimodular. And the simplest unimodular matrix is the identity matrix. Unimodular matrices are very important in so-called high-order transformations. That means loop transformations. What we will do is to express how we change the iterations, and we express that using one unimodular matrix. So all the parallelization and what possibly other optimizations, we express all this with one matrix. And with this matrix, we can then generate a new loop nest. As it turns out, we need to take the inverse of this transformation matrix. So therefore, it's essential that it's invertible. We have when we create a unimodular matrix, we use three elementary row operations, and that is reversal, interchange, and skewing. Reversal, simply multiply a row by -1. Interchange, interchange two rows of a matrix. And skewing, add an integer multiple of one row to another row. These operations are similar to the operations that are done in Gauss elimination. And well, they are called elementary matrices. So here are three times three reversal matrices. And here, for instance, if we want to reverse the first row in a matrix, we multiply this matrix with the other matrix, and then we have negated the first row, etc. To interchange two rows, we multiply one of these with the matrix. Or to add an integer multiple, we use either an upper skewing matrix or a lower skewing matrix. So, for instance, if we want to change rows 1 and 3, then we can pre-multiply matrix A with this matrix. And all the elementary matrices are unimodular. An echelon matrix is a matrix which, well, it's exactly defined here, but it's much quicker to just look here. And we have the leading number of zeros is either the same or increasing when we go from one row to the next. Okay, and why do we want that? Well, it's easier, just as in Gauss elimination, to solve dependency equations when we have expressed the equation as an echelon matrix. So, how to transform a matrix into an echelon matrix is the first we will see. We have this algorithm, and it takes a matrix, which it doesn't have to be square. It has m rows and n columns, and what we will find are two matrices, one U, which is unimodular, and another which is an echelon matrix. And this is always true. Oops. And we start with U being the identity matrix and S being a copy of A. So initially it's true. And then when we do something with S, we do the same on the other side. Okay, so what we want to do is to create an echelon matrix of S. And we do that one column at a time, starting at the leftmost column. So J determines which column we are working on, starting with the leftmost and going up to the last. And then the element that we want to become a 0 is Sij. Okay, so we find theta, which is the sign of the product of these two elements, and then Z is the quotient. Okay, and so we then subtract this from that row, and then we interchange them. So if we look at an example, we can start with this A, and so what we want to do is to first get the 0 there, and then there, and then there, and then we move on to the next column. So we start with the unimodular matrix, I mean the identity matrix with 4 rows and columns, and S is initially A. So we will first eliminate S 41, 31, and 21, 42, etc. Okay, so now the goal is to remove this -4, and we do that by finding the product and the quotient, and then we subtract this from the row above, and then we interchange these 2 rows. So these can be done with elementary row operations. And as we can see, the first thing is that we don't subtract anything, and then we, I mean Z is 0, and then we interchange rows 3 and 4. We do that both on both sides. So I mean this row is the one we are interested in, but we have to do the same operation on the left side, so that we always have U times A is equal to S. Okay, so next goal is, well, it's still the goal to make the element here 0. And we continue and find the following numbers for theta and Z, and we can subtract the current row 4 from row 3, and we get this, and we interchange them. Okay, and we repeat the process and get a 0 and interchange. So now we have achieved a 0 at this matrix element. What we do then is to continue. If we look here, we have done this, and we continue with the next row. Okay, I will not go into this into detail for every element, but we can eventually reach, so now the first column is finished, and we proceed with the second column, and finally we have found an echelon matrix and a unimodular matrix, such that what? U times A is equal to S.